Statistical distributions are used to model and predict the probability of a given event in a certain situation. Different distributions apply in different scenarios, and in S1 we are going to cover two of these: the normal distribution, and in this video, the binomial distribution. Whereas with a normal distribution, you'll almost always be told that something is normally distributed, the binomial distribution, you very often have to spot that it's binomially distributed based on the context of the question. And this comes down to key criteria that must be satisfied in order for something to be binomially distributed. The first of these is it has to have only two possible outcomes. This is quite often referred to as success and failure. The second one is it has to have a fixed number of trials. And the third one, it has to have a constant independent probability. Now let's have a look at a few examples of these to try and make sense of it. So the first one we have here, flipping a coin until you get a heads. Now this isn't binomial. It satisfies the criteria of only two possible outcomes, you get a heads or a tails. It's independent and constant, the probability never changes with a coin, but it's not a fixed number of trials because you don't know how many times you'll have to flip it in order to get that heads. On the second example, it says flipping a coin and recording the result after 10 attempts. Now this is binomial. Just like before, it's only two possible outcomes, constant independent probability, but now we have a fixed number of trials. It's specifically stating 10 attempts. So this would follow a binomial distribution. The third example here, a monkey in a cage is rewarded with food when a light flashes, record the number of times the monkey presses the button in 15 attempts. Unfortunately, this would not represent a binomial distribution. It has two possible outcomes, they press it or they don't press it. It's a fixed number of trials, you're specifying 15 attempts, but we cannot assume that it's an independent probability. For example, the monkey might get full, so he won't want to press the button anymore. Or he might cotton on to what's happening, so he might end up pressing it more, whereas at first he didn't realise what the button did. Similar in example 4 here, recording whether it rains or not each day of the week. Now it's only got two possible outcomes, and here it either rains or it doesn't rain. It's got a fixed number of trials because we've got 7 days in a week, but again, we can't assume it to be an independent probability. If it was raining one day, the probability that it's raining in the following day is increased, as opposed to if it was sunny the day before. Example 5, rolling a dice 20 times, recording the number it lands on each time. This doesn't follow a binomial distribution, and this breaks down on the only two possible outcomes, because obviously a standard die has 6 sides to it, so it's got 6 numbers, and it doesn't have two possible outcomes. Whereas the final example, rolling a dice 20 times and recording if it lands on number 6 or not, this does satisfy the only two possible outcomes, because it either lands on a 6 or it doesn't land on a 6, a success or a failure. Alright then, let's have a look at our calculator and how we can use it for the binomial distribution. Now the first thing we're going to do is going to go to stat, or number 2 on here, and you'll be presented with this here, and we're going to go to distribution, which is F5. Now you've got all the distributions here, and we're dealing with the binomial, so it's going to be F5 again, and you'll get 3 options at this stage. You've got BPD, BCD, and inverse binomial. Now the inverse binomial we're never going to use. The only ones we're focused on is BPD and BCD, and it's if we're solving different types of questions. So if we have a look here, suppose we want to try and solve the probability that x is equal to 2. Now this is going to be a BPD question. So I press BPD, it comes onto here. Now make sure that your data says variable. If it says list, you'll need to change that. Now the x, this is going to represent the number here. So x is going to be 2, that's what we want to make it equal to. The number of trials, this is our n, which in this case is 10. And the probability is 0.15. And I press that and I press execute, and I get the resultant probability for that. Alternatively, suppose I want to solve part B. Again, I'm going to go to distribution, F5, binomial, and this time, because it's less than or equal to, it's going to be BCD, so I press BCD. Same as before, except this time it's going to become a 3, the number of trials is the same, the probability is the same. I type it in and I end up with this as the answer. Let's have a look at some examples for our inequalities with binomial distribution. Let's take this first one, the probability that x is less than 3. Now the problem we have is our calculator only deals with less than or equal to. Now the best way to approach these is always to use a number line. So let's try and highlight what this is. So probability that x is less than 3, 0 satisfies it, 1 and 2, but 3 doesn't. So we're interested in this here. And this is going to be the same as the probability that x is less than or equal to 2. So that's what we'll put into our calculator. Let's take this next one, probability that x is greater than or equal to 4. So again, I'm going to try and highlight what this represents. So this is going to be on a number line, it's going to be either 4, 5 or 6. So what I can say this is going to be, well, this is going to be 1 take away the probability that x is less than or equal to 3, because this bit here represents the probability that x is less than 3, and 1 is obviously the whole result. Another example of this, if x is greater than 4, this time we're only dealing with 4 and 5, so we highlight them, and this is going to be 1 take away the probability that x is less than or equal to 4 this time. Over here we've got a dual inequality, so that x is greater than or equal to 3 but strictly less than 5. So let's try and highlight what this is. Well, it can't be 0, 1 or 2, it could be 3, it could be 4, but it can't be 5. So it's these two values here. And what this is going to be is this is going to be the probability that x is less than or equal to 4, which is going to represent all of these, take away the probability that x is less than or equal to 2, which is going to represent the ones that we don't want. Next one, it's strictly greater than 3 and 5. So actually when we do this, we only get the answer 4. Now one way that we could do this is we could say this is the probability that x is less than or equal to 4, take away the probability that x is less than or equal to 3, or you could just say it's the probability that x is equal to 4. And the final one, between 1 and 3 inclusive. So again, let's highlight what this is representing, which is this here, and this is going to be the probability that x is less than or equal to 3, take away the probability that x is less than or equal to 0, or equal to 0, either way. The formulae for the mean and variance of a binomial distribution can be found in your formula booklet, and once we have the variance we can just square root that to get the standard deviation. Now it's worth pointing out that if something is perfectly binomially distributed, then this will be the true mean of the population, and it will be the true standard deviation of the population. And we can use this fact to investigate properties of certain models. For example, if we have a look at this question here. At the start of the question it says it's assumed that the probability that Miss Viewer sorts letters incorrectly is 0.06, and that a sorting of a letter is incorrectly is independent from letter to letter. It's that word independent is key. Now in this question we've got a fixed number of trials, there's two possible outcomes, so in this case it's incorrect or correct. So this idea of independence, if this is correct, then it's going to be binomially distributed. And the question goes out like this. In part 3 it says calculate the mean and variance of the numbers of letters sorted correctly. So this is where we're going to use our formula from the binomial distribution, and we'll get what we'd expect the true mean to be and the true standard deviation. And then in part 4 it's going to be taking a random sample, and it gives us some data here. It says of this sample, the sample mean is 112.8 and the sample variance is 56.86. And what it's expecting you to do is compare these values to the values that you calculated in part 3. Now if they match up quite nicely, then that means that the binomial model seems to be a good fit, and you can assume that it is an independent probability. Whereas if they don't match up, that means that it is not a binomial distribution. And if we go back to earlier on, there's two possible outcomes, there's a fixed number of trials, so it must be that issue of independence that's breaking down. And this is why it's saying on the question, comment on the sorting of a letter incorrectly is independent from letter to letter. And I think in this question you'll find out that as they don't match up, we assume that it is not an independent event. If we have a quick look at another one, same sort of idea, and a lot of the binomial questions take this idea. They get you to calculate the mean and variance if something being binomially distributed. That's in part B. And then in part C, it's introducing some sample. And from this sample, it wants you to calculate the mean and the variance of this sample. And then it wants you to do a comparison. So in part B, we've got the true mean and population if it's a perfect binomial distribution. On part C, we've got the sample of the data. And if these match up, then we assume it's binomially distributed. If they don't, then it isn't binomially distributed. And again, it will be that idea of independence that is breaking down. Okay, the first thing you want to remember is the conditions for it to be binomially distributed. That's 2 possible outcomes, a fixed number of trials, and a constant independent probability. The second is your notation. You'll need to write this down in a lot of examinations, so don't forget it. X is distributed binomially, NP, number of trials, probability of success. The third one is still able to answer questions when there's more than 2 possible outcomes. So you can still treat it as a binomial distribution provided you look at it in a certain way. So for example, in this one here, it's exactly 4 red loom bands. Even though there's 6 colours in total, it's either red or not red. And you can see the binomial probability has changed. So it's 0.18, in part 2 it's 0.15, in part 3 0.5, and so on. So you can still attempt questions where there's more than 2 possible outcomes as long as you approach it in this manner. The fourth one is a similar approach. This is changes in probability or the number of trials. So if we take the left hand side first, in June 2011, we can see in part A it's saying determine the probability that the number of balls in a box which fail a bounce is. Now earlier on the question it said there were 10 balls in a box. So this was distributed binomially and our n was 10. Now later on in part B it says determine the probability that in 5 boxes. So this is where you need to realise you're changing your conditions. It's now distributed binomially, but in this case your n is now 50. So always look out, they tend to put it in bold for a reason. And in the right hand side is similar to what we've seen here. Throughout this question the probability is changing and you need to make sure that you're indicating that as you go through. The fifth one is your formulae for this. Obviously the mean and the variance, they're given to you in the formula booklet, and the standard deviation you can get from square root and the variance. And the last one is comparing your expected mean and standard deviation with the sample mean and the standard deviation. Now I went through this earlier on in the video, so go back to that if you want to, but make sure you fully understand how to do that because there's a very high probability that you'll be asked to do that in the examination.